Hello everyone. Good evening. A very warm welcome to everyone on day 6 of our workshop that is on systematic review and meta-analysis organized by Integrated Foundation Uttarakhand and Integrated Association of Medical Basic and Social Scientists in collaboration with National Institute of Nursing Education PGIMER Chandigarh and AIMS Rishikesh. We appreciate your active participation and look forward to another insightful sessions today. We are honored to have with us Dr. Ashok Kumar, a distinguished expert in research methodologies and data analysis. He will be speaking on meta-analysis using R Studio software, forest plot, means including forest plot, meta regression. Dr. Ashok is a faculty member at the National Institute of Nursing Education, PGIMER Chandigarh, with an extensive research background. He has over 50 national and international publications, has presented at prestigious conferences worldwide, and has guided multiple research projects, including ICMR-funded studies. He has also been recognized with numerous awards including the Stroke Rehabilitation Award Best Researcher Award for his contributions to medical research and biostatistics. Without further ado, I now invite Dr. Ashok Kumar to take over this session. Sir, please.
Thank you, Dr. Priyanka, for nice introduction. So without delay, because today is 2 sessions, okay? So without wasting time, I have sent in SRMA group there is video to make and some like files, R files, and Excel file and one Word file, okay? So I'm seeing that in SRMA group, some participants are facing, or I think many participants are facing uh, to install read XLX package. So no problem. Okay, some because it's a R, it's a free, so there is some problem. So when you search in Google, I think one participant already sent a second way how to install. Okay, so it's very good thing. So like we have to search on Google and Crane website of this R, okay, CRAN, Crane, okay. So we got the solutions for this. So without wasting much time, I'm going to share my screen, okay. So I think my screen is visible, ma'am.
Yes, sir. Yes, sir.
Oh, thank you, thank you, thank you. So I already opened this, okay. Some are facing open this I think R file which I have sent. You can see on my desktop I have made a SRMA folder, and I have put all these things which I have sent in SRMA group in this. You can see here, okay. So first, what you have to do, if you made this, okay, I think you have made, and all of us made this thing. It's very simple. So what you have to do, you have to click this one group proportion here. This is a R file. You can see this is Excel file, one group and two group. So when we click this one group, this is a data extraction, okay. And I used and I some modify this file for, like yesterday session, Dr. Maninder Deep Kaur explained us about how to extract data in Excel. So I modified, okay, this is a hypothetical data. I have modified, ma'am, enter this in first row, okay, or in author, they have entered 5 studies, first name of the author, okay, and that is the name of the first author and year, you can see here, then country, then design, then this is a male percentage in study, okay. So we can write down male percentage, male or female. Ma'am have written male and female. But in this condition, male, gender, under gender column, there is the male is how many male and female, how many female. We cannot analyze in that format. So what we have to do, we have to get male percentage or female percentage, whatever you want, you can do. Okay, so this is a male percentage because we can do analysis on the basis of this. Okay, then this is an n is a sample size of, I have some modified this. Okay, and then this is a hypothetical data, and this is e means event or prevalence. So prevalence of, and this is a good knowledge. Okay, good knowledge of antimicrobial stewardship among healthcare professional. So this is a, so out of 64, 38 healthcare professional have good knowledge. Out of 15, second study, you can see 30 healthcare professional have good knowledge like that. Okay, so this is data sheet, you might understand. Then this is knowledge, you can see here left side below the sheet, name of the sheet, you can see knowledge underscore p. P means prevalence of knowledge, good knowledge. Okay, you can give any name, whatever you need, you can give, there is no problem. And this is second sheet, you can see this is a mean underscore knowledge, yani mean of knowledge score. In some study they have given only percentage in the form of proportion. In some study they have given mean and SD of the knowledge score. So we have to enter data. So this is also hypothetical data I have entered. So how I can enter? Only 3 study have given mean and SD. You can see this is a mean column, this is a SD column. Okay, and only 3 studies out of 5 they have given. So this is like author, country, design, male, percentage of male, then mean of knowledge and SD of knowledge. Okay, I have given, you can see in third there is a code. What is like something like, you can see n is equal total sample size, is a prevalence of good or very good knowledge. Okay, means how many participants having good or very good knowledge. And here in this sheet you can see here mean of knowledge score, or SD means standard deviation of knowledge score. We want here, we have left one thing more, that is we have to enter here. I have left, you can see here, we need n also. Okay, we need n in this. So I have create one column here. Okay, and then insert, and then I have to write down n is a sample size of 3. These studies, Hairawati. Okay, so where is these 3? 1, 2, and 3. These 3 I have to copy, then I have to paste. Okay, so these things we need. One group mean like mean, there is no comparison. So one group mean forest plot if we want. This is a descriptive study, observational study, or cross-sectional study, something like that. Okay, and this is a one group proportion study. Okay, so this is a prevalence study. Okay, it may be, for example, like for example, I want to give another example, hypothetical example. For example, here diabetic patient. Okay, this is a diabetic patient, or here like neuropathy in diabetic patient. So this is an event, neuropathy, retinopathy. So this is something like that. Okay, these are the diabetic patient, and out of which these diabetic patient, how many have neuropathy? Only one outcome, neuropathy. If you have second outcome, retinopathy, you have to enter here. Okay, you have to enter here for retinopathy. Then what you have to do, you have to do some changes here. Like you have to write down E1, that is for neuropathy, and here E2. Okay, E2, whatever you can, you have to some like change E1, E2. Okay, E2 means that is for retinopathy, and you have to write down here. So this is just I will delete it. You can I think you have got this. Okay, so this is my file, I will save it. Okay, and now I'm going to start hands-on. So what I have to do, I have to click this one group proportion prevalence, something like that. Okay, so I will I have to click this, just click this. Okay, this will, okay, it's opened. You can see here, this is, maybe there is no need of this for me. So I put here. This is, you can see here, this is one group proportion file. This is opened, and many participants face this problem for read XLSX, and then one participant sent a beautiful, I think, answer. We can install according to this, because R is a free and it's updating. I think in 1 year it's updating 3-4 times. So sometimes this is for older version. Okay, for latest version it's not working. I have both older and latest, so it's working. So when you do work on this R, you will get it more and more. Now, first thing, okay, we have to set working directory. Okay, so what we have to do for this, we have to go. I have sent already a video. Again, I will show you. Click session here. You can see here, left upper corner. These are the here session. In session, you can go to set working directory. This is our first step to do on RStudio. Okay, then you have to click choose directory. I think it's very simple, and please don't ask me for repetition for this. It's very simple. So click this choose directory. Okay, so this is here, and where I have to want to set SRMA folder desktop. So I have to see this is desktop here, and this is SRMA folder. I have to just click here, just okay. I have to click here. You can see here, this is a desktop here. Okay, it will automatically change. So what I have to do, I have to click only once, not twice, only one. Click here. This SRMA folder come here. Please don't click twice. On single click, then open. Okay, so this command you can see here in console. This is a console. This is a R script. Okay, so this came here. It means we have set our working directory. Number one step we have done. Then what you have to do, you have to install all these packages. I think you have installed all these packages, but you have to run like these packages. Every time you have to run. So what I have to do, I can click this. Okay, if anyone is facing any problem, okay, we will resolve. No issue. So select this, and then because I have already installed these packages, many participants have already installed, but every time we have to run to load these packages, library, read Excel. Okay, and this is, you can see here, this is library read Excel. Okay, and this is install package read XLSX. So both different package. If you are not getting success to install this package, then what you have to write down, you have to just write down here, install here in inverted comma, you have to write down READ XL. Okay, then you have to install. I think you might get success in this. So after this, after installing this package, because I have already have these packages in my RStudio, so there is no need to install, but you can install this. You have to run. So for run, you can click in this line anywhere. Okay, and then you have to click run. It will work. Otherwise, you can select this, and you can select this. Oh, sorry, only this package. You can select this and run. Otherwise, enter and enter. Okay, enter. You can here. So it's a very simple. Select this and run, or you can click here and there and then click run. Okay, so I have to load these. I have to activate these. These are the packages. Okay, so I have to click select all. I can select in once and then click run. So what happened? It's no problem. There is no issue. Okay. So, okay, all packages activated. You can see here, all packages activated. Then I can perform meta-analysis. For meta-analysis, I need file, Excel file. Okay. So I have to load that Excel file in RStudio. So from where I can load, please see this. I have to, you can see here, this is the environment. Okay, in right side. there are 4 pens. Okay, one pen, this is our script. Okay, this is our console. You can see here, this is a console. Left below, right upper, this is an environment, and this is a plot file, something like that. Okay, so here you can see in environment there is a import data set. So from here we can import Excel sheet. Okay, even SPS sheet, even SAS sheet, even status sheet we can import in. So what we have to do, we have to click this import data set. These are the files. So we have to click from Excel, because we have saved this data in Excel. If we save in SPSS, SAS, these are the statistical package, and Stata we can import even though. Okay, there is no problem. Excel is very simple and free of cost, so we can import from Excel. We have saved data in Excel. Sometimes what happen when we click here, so there is a message, this package is not installed, please install it. So you have to click yes, and then you will get this package, read Excel package. So there is no problem. Okay, sometimes it happen if you like open first time or import first time Excel, so this will come. So because I have already installed read Excel package, I think I might not get this message. So I directly get this message, import Excel data. Otherwise you will get that message. Otherwise you will get message, read Excel or read Excel package is not installed, please install first. So what you have to do, you have to have internet, good internet speed, and you have to click yes. So that package installed on your will be installed on your R Studio in your laptop, and then this will open. Okay, then what you have to do, you have to click here browse. Okay, you have to click this browse, right side you can see, you have to click this browse. If any like participant facing this, please see this. Okay, then we will solve this issue, there is no problem. Then where in this one group I have, this is a 2 group Excel sheet, this is a 1 group, this is a RCT. Okay, and this is 1 group for antimicrobial stewardship. So I have to click this, I have to select this, then I have to click open. So you can see here in right side, left side, there will be some changes, and here also name, left side below you can see there is a changes something. Okay, so I have to click open. So you can see here, this is a 1 group, this is a default sheet, and this will come, you can see this will come here. Okay, this will come here, and then we have entered data. This is a sheet, default sheet. Okay, this is a sheet, and actually I have to like import this sheet. Okay, proportion sheet, this is a proportion, but if I want to import that mean or SD sheet, so what I have to do, I have to click this sheet default, then I have to click this mean knowledge. Otherwise I want to like import this time knowledge prevalence, so I have to click this will open. Oh, okay, there is no problem, and this will come, the changes will come here, you can see here. So what I have to do, I have to click import. Okay, so just click import, this Excel sheet will come here. Okay, so there is no problem, this Excel sheet will come here, you can see here, this Excel sheet will come here, you can see N and E, this all author and something like that. Okay, and you can see here, this is the command of this came here. Okay, so no need to do. Okay, it's okay, there is no problem. You can see I have given this name 1 group, I have given this file name as 1 group. Okay, but on R Studio when we work, then I have to give name this, because this is data sheet, I want to give data something like that. It is given as default as a 1 group. So what I have to do, if you want to leave it, you can leave it, there is no problem. But because if I want to change this 1 group, because I have given this read Excel file 1 group and knowledge prevalence, name is 1 group I have given. I want to change. So what I have to do, I have to select this. Okay, I can select this from here to here. I can select this. You can also select, there is no problem. Okay, then Control C. Okay, then where is my one group? This is one group proportion. Okay, so I have to click this. Okay, these things came here. So I have set working directory. Then I have to load data, and for load data, I have to copy paste here that thing. This will come like that. So what I have to do, I have to remove these you can see there is a cross means there is some unexpected signs, something like that. So I have to remove this greater than or less than this mark. I have to remove here. So I will remove it. Then I will remove this also. And this is a plus sign. You can see here. I will remove this also. Okay, you can also remove this. So this is okay, this sheet. So I want to give this one group as a data. Okay, so what I have to do, I have to click data. If you don't want to do, there is no problem. Data. Okay, this is just give data. Then run again. This run again. Okay, so first it was given as one group name. Now it will be converted into data. Okay, so then what we have to do, or otherwise what we can do it, okay, we leave it, or one group will leave it. There is no problem. Okay, we leave it as one group. Okay, name of the data sheet is one group. So this is one group. Okay, it's okay. Then we have done the, I can remove it. So okay, this is till we have done our 50% work has been done. And from this to this, from this perform prevalence meta-analysis, from this to this, you can see here, it will take only 2 seconds, only 2 to 5 seconds to do perform meta-analysis. If we have done this work till here, okay, main work is this. So if we have done this work, this will take only 2 to 5 minutes, 2 to 5 seconds for me. But I will explain you one by one. Okay. So perform meta prevalence. So you have this file, I think. So what, there is no problem. What you have to do, you have to, this is, I have given, this is a name of this function. Okay. This is name of this function, meta prop, and what we are performing, we have given name of this m.prop. You can give any name. There is no problem. You can give any name. I have given m.prop. When you work on RStudio, you will get automatically, okay, it's m.prop, it's okay, there is no problem. Okay. Then this is function meta-prop, meta-analysis of the proportional studies. Okay. Then these are the arguments. Event, these are the default argument. Okay. Event, n is a sample size, s study labels, data, method, summary measure, fixed effect model, random effect model. Hacken is something else, no need to do anything about. And this is a title. Okay. This is. So if you want more about this meta-prop function, if you want to read anything about it, so what you have to do, in this here left side below, there is a help. Okay, this is a help. So what you have to do, you have to click this help, and then you have to type here meta-prop, meta-prop. This is meta-prop. You have to click this meta-prop in help. Okay, file plot package help, and then click help meta-prop, and then you have to click enter. So in meta-prop, you will meta-analysis of single proportions. You will get each and everything here. Okay, you will get each and everything. These functions, these are the functions you will get. I cannot explain each and everything here. Okay, when you do first and meta-analysis, then you can understand one by one. Okay, in 1 hour, it is impossible for everybody to understand. But you, when you, this is this is command. Okay, This is command, this meta prop or everything. Okay, this is a meta. You can see here meta prop, and in bracket, this is a event, this is a and this is a study lab, this is a data. We need only this. Okay, there are other functions. Okay, we need only this, something like there is no need of anything. We need only this. But the I have given you more and more things for this. This is SMEs in summary measures. Okay, so here event means prevalence or proportion. In that Excel sheet, what we have given here, so, okay, I'll open this Excel sheet. You can see here I have given E. Suppose if you have given anything, okay, like prevalence, here, okay, prevalence. So what you have to do, you have to write down here, where is my, you have to write down here prevalence. But right now, please don't change. Okay, you have to write down here prevalence. Okay, event is equal to prevalence, because you have, because and I have given is E. So this is when you do work on RStudio, you will understand. Small name, small, there is no any capital. You can see in this there is no anything capital. Everything is small in letters. Okay, in and I think minimum letters I used. Okay, you can see here minimum letters I used. Then this is event is equal to E, n is equal to sample size. You can see here in this, everything is explained here. This is, you can see here. Event is a number of event. N is a number of observations, total of study lab is an optional vector, study labels. Okay, authors something, data is a data, and everything else here you can see. Okay, so no need to like include all and each and everything, and no need. Then this is a study lab. Study lab we want are like meta-analysis according to author, because when we want to get forest plot, we want according to author. You have seen. Okay, so this is author. I have study lab means study labels. I want this according to author. Okay, you can see here this AUTHOR in small letters. So I have to see here. Okay, this is author. Okay, very good. Then this is data. Data is DAT, but you have to do some corrections, because I have made this as a one group. So I have to control C, and I have to make this now here one underscore group. Okay, you have to do this much changes, and there is no need not to do anything else. Okay, then what I have to do, I have to click anywhere here. I can select this, no problem. Okay, then I have to click this run. I will select this from here to here. Then I will click. If you want to give title, okay, prevalence of good knowledge, or prevalence of neuropathy in diabetic patient, something like that. Okay, prevalence of heart attack in COVID patients, you can give anything according to your like PICO or research of questions. So I have to, what I have to do, I have to select this, and then I have to run. So what will happen? You have to see in console. This will happen. Okay, there is no problem here. They are what they are saying nowadays. Warning, there is a warning. Okay, just warning. But okay, use argument common instead of fixed, and use argument method dot random dot ci instead of hacken. So there is no problem. Okay, there is no problem if we do according to this. So what we have to do, we have to click this fix. Nowadays it is common. Common means fixed, same, synonym. Okay, in RStudio it's a synonym. Okay, in like meta analysis, so I can give common. Okay, is okay, then I have to click this. So what when I perform, I think again I will perform, then this argument warning I think will not come. Okay, then I will perform again. This only single warning came, because I have corrected this, fixed to this. And then when I correct this, so this will in place of hacken, when I use this will automatically gone. So okay, no issue. This is a method of confidence interval. Okay, so I will correct it, no problem. Then click OK. There will be no any red sign. There is no warning message. If I let these fixed and Haken, it is okay. There is no problem. Okay, but for this demonstration, I remove and I replace these things. Our studio will give warning and messages in red color. You have to do this. You have to do this. You have to do this. Suppose if I place here in study lab author like this, okay, author like this, okay, then when I perform this will give a clear cut message. Object author not found. You can see here. Because in my data sheet, there is a author in small letters. But here, what I have performed with the capital A. So what I have to do, I have to see my data sheet. Oh, okay, I have given this author. So then I have to change it. Okay, then I have to change it. Then I will perform again. Every time you have to perform after changing. So it work. Then what I have to do, I have to click this summary. Here summary of metaprop is m.prop. This is a function. This is a name of this function I have given. Okay. Then I have to click summary. Summary you can see here. This is a spelling there. I have to click anywhere, or I have to select. Then I have to run. So this is our result of meta analysis in this. So sometimes we are not using this mainly. What we are using forest plot. So how to make forest plot? Okay. So what I have to do? This is forest plot. Simple. Forest in bracket m.prop. Okay. So what I have to do? I have to click this. This is a function forest and prop. I have given already. So there is no problem. If you are like these command are running, so there is no problem. You will get forest plot. And here you will get forest plot in right side below. In plot section, you will get forest plot. Okay. So we will see here. So when I click here and then I run this. Okay, I'll see. Okay, I got this forest plot. Then when I click this zoom, okay, you can see here. When I click on zoom, then this will forest plot. So I think for many participants, this is first forest plot they have created, if they have created successfully. Okay. So congratulations to all who got this forest plot first time, and who are not getting this, no problem, we will get. Okay. Try makes human perfect, something like that. So what is all the thing? Heterogeneity, I square, this is a tau square, this is p value, these are the study name in this forest plot. You can see these are 5 studies with this. These are the events you can see here. These are the total sample size. This is for each study prevalence with 95. This is a proportion you can see here. Okay, this is a proportion you can see here. 38 out of 64, there is a 59% or 0 point. This is 95% of, and this is a weight of the study. Okay, this is a weight of the study, and weight of the study depend on sample size and like proportion, how much proportion and sample size. So you can see here this 148, 251, 180. The sample size is it's visible or not? Ma'am, you can see. I think it's visible or not. I'm not getting this. Okay. Oh no, okay, it's visible. Okay, thank you. Okay, yeah, you will get some no issue. You will get these things. If you get this, then you will get success. No issue. So this is okay. You see this study, Dr. Priyanka, this forest plot is visible or not? Can anyone just message on just okay? Visible, sir. Okay, thank you. So you can see here these the with the large sample size. Okay, you can see here the weight is large, 20, 22, 24, 23. This is the power of study, something like that. Okay. So large sample size, power of increase, and weight is also increase, something like that. These are less sample size, 64, 50. So weight is less. Okay. This is random effect model. You have to remember roughly. This is a I square. I square फिर heterogeneity. Dr. Supal Kaur ma'am taught you in her lecture in session beautifully about I square. So it is in percentage, 0 to 100, its value. So roughly you have to remember, if I square is greater than 50%, we have to use random effect model. If I square is 50 or less than 50%, we have to use common effect or fixed effect model. You have to just remember, its I square is 85.8%, it's more than 50%, we have to use random effect model. And what is random effect model, we will discuss anything any other, because this is if you have to just remember, if 50% more than 50% I square, we have to use random effect model, or if I square is less than or 50%, we have to use common or fixed effect model. And you have, this is a pool effect model. This is, you can see here in proportion, each study has this much proportion of good knowledge, and this is a pooled, this is a pooled prevalence or proportion of good knowledge, 53%. Okay, this is a pooled. So 53% of the participants, this is a pool effect, we can say. Okay, this is a pool effect size, we can say here, and this is a diamond. You can see here, this is a diamond in the shape of diamond, and you can see there is a dot line here. You can see here, this is a dot line. So this is a 0.53. This is a effect size of, okay, overall effect size. It's called overall effect size, 0.53. It is a 0.53. You can see here scale, you can see here 0.4, 0.45, 0.5, and 0.55. So here it is a 0.53. So this dot line is a on pool effect. Okay, and this is the confidence interval of pooled effect, 0.43 to 0.63, 95% confidence interval. It is a 95% confidence interval. Okay, so this is 95% confidence interval. This is a pooled effect of overall effect, we can see here. This is a like a forest plot of one group proportion study. But this is not according to like it's not looking beautiful, something like that. If you want to add something else, so you can do. So what I have to do, I have to cross it, no issue. Then I have made, I want to save this forest plot, then I can save this. So this is another, this is forest function. You can see here, this is forest, this is also forest, and this is mprop here, and these are some other designs. These are some other designs. Pooled event is true, prediction is true also. Nowadays in literature, they need prediction interval, they need. And what is prediction interval, we will I will tell you, no issue. This is a layout, we need Raveman 5, because Raveman 5 is most popular. Earlier it is, or right now it's the most popular software for meta-analysis. So some general need in this form layout. This is a text name, is a pooled prevalence. X means x-axis label is good knowledge. When we perform this, what you have to do, you have to just, I have given you already, you have to just select and click run. You will get this beautiful. Okay, here, then I can, when I click this zoom, you will get this. So now what you have to do, you have to just click, and you will get all the thing here. This is in red, there is a prediction interval. You can see here. Nowadays, like journals want this prediction interval. It means overall, like there is a effect size varies between the, like in studies, okay? Between studies overall, from this to this. So this is a prevalence interval, and everything is same in that, like 85.8% I square. This is a good knowledge. This is some beautiful, you can get it. Okay, this is a inverse variance, something weight here, event, yeah, and then random 95% CI, something like that. Okay, and if you want to save this this like in PDF format. So I have given already this command. This you can see here, this here to here, this is similar. This and this is similar, you can see here. This is this similar, okay? This one and this one, both are similar. But I have added, I want to command to save forest plot in PDF. So I want to save in PDF. So I have to give PDF file name forest plot knowledge. You can give any name dot PDF. I have given you. You can change from here to here. Only from here to here you can change. Okay. Then width, then height you have to. Then this function is you have to do also. Dev dot off, and this is bracket. No need to write down anything in bracket. Then what you have to do, you have to select all three. Okay, you can see here, you have to select all three and you have to run. Then what will happen? This will save forest plot in our working directory. So where is our working directory? SRMA folder on desktop. Okay, we will see here, click run, and this will come here. Okay, if this come here, you can see here below this in console, this will come here. It means it will work. There is no red line, red signal here. So our command work very well. Okay, then I have to see in SRMA folder, and you can see here, this is my forest plot knowledge. I have saved this. Okay, when I click this will open. This is my.
So, apologies for the interruption, but due to time constraints, we kindly request you to conclude the session within the 10 minutes.
Yes, ma'am. Yes.
Thank you for your understanding.
Yes. Okay. Thank you, ma'am. Thank you. So I have saved this. Okay. Then if you want to save in PNG file, something sometime like journals want in images file or PNG file. So this is just command. You can see this is common. This is same. Okay. I have highlighted this. This is the same, but changes here only PNG file, something like that. Okay. I have given you. So what you have to do? You have to select it and you have to run. No need to do. And this is okay. This came here in console. You can see it's work. There is no red signal. And I can see in my SRMA folder, this is in image, and you can see here in image. Oh, very beautifully, very good. Okay. And if you want to interpret it, you can interpret. I will show you, okay, now, because time shortage, I have given you all the things. If you want to do funnel plot, okay, something like that. Or if you want to do DOI plot, nowadays DOI plot, they need journals. So what you have to do, this is prepared. And what is this is m.prop. It's coming from here. You can see here, it's coming from here. I have given m.prop. So it's coming from here. And everything I have given you. So what you have to do, you have to click from here to here for DOI plot, and you have to click run. And if you want to more about DI plots, so what you have to do, you have to click help, and you can search DOI plot, you will search anything. Okay, otherwise you can do on Google, you can see on Google. So there is no problem. So what you have to do, you have to click this from dev.off till you have to select, and then you have to run. It will, okay, there is no problem. You can see there is no signal on console, and I have to see my like folder working directory. This is a DOI plot, and in DOI plot you can see here, this is a LFK index. For if there is no public, it should be close to 1. Okay, should be close to 1 value. Then it's like there is no publication bias. Okay, but now like in general they want funnel plot, so there is no problem. We can get funnel plot. So what I have to do, I have everything I have given. You have to just select from here to here. You can click run, then you will get funnel plot. On these are the warning message. So after this warning, you will get funnel plot. There is no problem. Funnel plot. Okay, this is funnel plot. You will see, and this is beautifully funnel plot you will give. Only one study is from this, I can say this triangle outside. So I think, okay, four studies inside this. So I think there is a little bit publication bias, not more. So we can, okay, and this is, and then what you have to do, you have to, this is Agar plot also. Nowadays it's like Agar test they are using. So this is command for Agar test. What you have to do, you have to select, you have to click, and this p value of this will come here. Only this will come here. This p value of this Agar test is if it is less than 0.05, it means there is a publication bias, and if it is more than 0.05, there is no publication bias. You have to remember this. So here p value is greater than 0.05, so there is no publication bias. It's a quantify, but in funnel plot we cannot quantify it, but we can say, okay, there is a minor publication bias, not there is a moderate or severe publication. But using this Eggers test, okay, like t-test, chi-square test, something like that, its p-value is coming here, 0.1741. So there is no publication bias. We can conclude, we can write down in our manuscript, okay. Then I have on now I will not like go in detail, something like that. I will go, I think 5 minutes or 10 minutes I will take, not more than. I will stop 7:05, okay. 7:05 I will stop. Now I want to do for two groups, okay. One group mean you will do. One group mean you will do. I have given you like commands. Now two groups. So two group for proportion, okay. Two group for proportion. So this is two group proportion comparisons. Command I have given, it will work for all meta-analysis in this world. For two group proportion, it will work. There is no problem. Okay. So what I have to do, I have to click this. So this is opened. Two group proportion. I have installed all these things. You remember, I have installed, so there is no need to install this. I have activated already because I didn't close this yet, not close my RStudio. So no need to again load this packages. I have already working working directory. I have already set. There is no problem. The main thing is I have to import data sheet, because two group proportion in not in that data sheet or Excel sheet. It is in here two group. This is second data sheet. Okay. In second data sheet, when I will open it, it's on effectiveness of I think educational intervention on lymphedema patients post something like that, breast cancer survivor or something, as Maninder ma'am last class explained how to extract data. So this is I have I think you got this, what is all the things, because Maninder ma'am, and this is a total sample size. This is a and in IG means like intervention group, and this is CG means control group. Mean age is intervention group. SD of age is intervention group, something like that. And this is main thing, because this is a comparison of proportion in two groups. So this is E means event, IG means intervention group. Okay. So this is two. What do you mean by two? And you can see here in data sheet here left side, you can see this is a lymphedema. It means this is a prevalence of lymphedema. Okay. So E means lymphedema, prevalence of lymphedema. IG means intervention group. So what this is two patients have lymphedema at 3 months. Okay. Out of 47 in intervention group. Sorry, intervention group. Okay. And ECG means event of lymphedema in control group 4. So 4 patients have lymphedema out of 56. So according to this file is prepared. This is a hypothetical data again. You have to prepare this file. Okay. Then what we have to do, we have to import this file from in RStudio. Okay, so just I can import it. So what I have to do, this is, so what I have to do, I have to go in import data set, then from Excel. Okay, this is from Excel. This will open import Excel data. What I have to do, I have to click browse here. This will open automatically, SRMA open. This is working directory. Okay, then click to group and then click open. This will come here, and this is a sheet. You can see. Okay, 1 minute. I think. Sorry, there is no charging in laptop. Sorry. Yeah, this is data sheet. I can see here. I can view this. Okay, I need this data sheet. There is no problem. Yes, this. Then what I have to sheet, I have to here sheet default, I have to click lymphedema. Okay, if you want to click, you can click. But for days, this is the days disability in arms, shoulder, and hand, you have to click this. But lymphedema, it's in default. Then I have to click import. So this data sheet will come here. Okay, it's working, I think. Okay, I'll take only 5 minutes more, 4 minutes. It's 7-1. Okay, this file came here. You can see here. Okay, this came here. So what I have to do, again, I have to select this from console, Control C, and I have to click. This is a two group proportion comparison. I have to click this. This command came, load data sheet. What I have to do, sorry, I have to control paste. So this came here. I have to remove all these things. Okay, which gave error. Oh, sorry. And then I have to click this plus. I have to remove this plus, and I have to. So name of this is two groups. So I'll keep it two groups. So what I have to do, I have to remove this data one. So two groups. Okay, this is two groups. I will not change. Then this is meta analysis. So everything is here. You can see here. This is a meta bin package. Meta bin package. Meta bin like function. This is a meta bin function in metaphor. So and earlier it was a meta probe, proportion of meta analysis. This is a meta bin. Meta bin means binary outcome. Meta analysis of the binary outcome. Yes and no. Lymphedema, yes and no. This is a meta bin. Okay. And these are the event.e. What do you mean by event.e? This is the event.e. Okay. This is the event in experiment. This E is experiment. This E is experiment. This E is control. You have to remember this. So I have to put E_IG because I have given this name, column name, E_IG. This is N.E. N dot means sample size in intervention group. So this is default. Okay, these are the default. So we have to change only this. We have to change only this. Okay, you can see and leave it. This is method inverse variance. And here data we have given data one, but actually what we have given two groups. So what we have to do, we have to click Control C, and then we have to just change it, two groups. Okay, then it will work. This is summary measure is R means relative risk. If you want it, this is a command, this is a random, this is a prediction, this is a method tau, this is a like ML. These are the functions of this. So you can, if you want to learn about, you can click help and you can type here meta bin here. Okay, meta bin. Then you will get anything about this. Enter. This is a meta bin, binary outcome data. You will see and you can learn more and more about this. Okay, then leave it. If you want in odds ratio, this is a relative risk. If you want to do in odds ratio, what you have to do, you have to just click here OR. OR means odds ratio. Okay, so I have given you in second also in odds ratio, but you have to, we have just modify m.bin and 1 because this is a m.bin, m prop, m bin. Okay, You can give any name. Okay, no problem. M dot bin for relative risk, you can perform this. So what you have to do, you have to click this and you have to run. Okay, there is no problem. Everything is coming. There is no red signal here. Then summary M dot bin run. Oh, this came here. This is our meta-analysis. Okay, with the relative risk you can see here. And but we want in the forest plot. If I want to do in with the odds ratio, okay, this is OR. So what I have to do, I have, because I have written data 1. Okay, you can see I have written data. So what will happen? I select this. Okay, here. Then when I click run, this automatically come error. Object data 1 not found. Why this problem? Because I have given data is a 2 group. Okay, so what I have to do, I have to just 2 group. Okay, these 2 groups. Then when I select it and perform it, it will work. There will be no any error. But this time it will in odds ratio, summary measure. Then summary M bin 1. I have given 1 here. You can see I have given 1 here. Then what I have to do, I have to click this summary. Okay, this is okay. Then I have to click this here. Then I run. It will come summary measure for odds ratio. So there will be difference. Okay, in odds and relative risks, there is a difference. Then this is forest plot for, okay, so what you have to do, you have to click just, you have to select and you have to click and you can see here. Okay, this is for like this is a Jadu, you can see here. We can clear all the plot. Okay, broom, and yes, so all this side cleaned. So I want to show this forest plot. So just now there is no problem. We can get this forest plot. It's a forest plot. When we click on zoom, this will come. This is odds ratio. You can see these are the 4 studies. This is experiment events, control event, total N event, and N total N. You can see this is a odds ratio. This is, you can see here, this is for like single study effect size. This is 95%. You can see here. You can see here, it's a very interesting thing. Okay, these are odds ratio 95%. This is a pooled effect. You can see here in common effect model and random effect model. I have used both in this common effect, random, and you can see here in heterogeneity, I square is 0%. It's a very good thing. Ideally, it will not happen. 0%. There is no heterogeneity. Very good, but ideally it will not happen. It happens. It's very good thing for you. Then you can see here common, if I square is 0%, then common effect model value and random effect value is equal. You can see here. Okay, this is same thing. The diamond is, you can see similar, identical. Okay, and this is a prediction interval, and this is 1 is for odds ratio. This is for null effect. Okay, there is no effect in 1. So you can see here in intervention group, the lymphadenopathy is 0.42 times compared to control group. So if we are given educational intervention to the patients, so there is a chance of lymphadenopathy is only 0.42 compared to 1 in control group. 1 in control group. So in intervention group, this is 0.42. It means there is a less chance of this. And this is a confidence interval. You can see here. Okay. And this confidence interval never cross 1. If cross 1, it means there is no effect. Control and intervention both are same. Okay. Then these are the other things you can, what you have to do, you have this command, you have click this, you can save this. Okay. Run. This will happen because I have used dev.off. Then you can see in your 2 group proportion comparison, where is forest plot? This is forest plot M1. You can see I have given name. I have given, this is M. Okay. I have given file name forest M1. You can see. So I will see forest M1. Then you can see this. Okay. So I can see here, this is forest, beautiful forest plot. You can see here. Okay. And I think I should stop here. This is okay. It's not coming. It's cutting. Okay. Side from side, it's cut. So what you have to do, you have to change dimension. It's very good thing. So what you have to do, you have to change dimension. So here dimension is given 10 and 3. So what I can do here, 20 and 10. Okay. So these are the, then I will save, and I will want to see what will happen, because I don't know even what will happen. So here I will see it's coming or not. I will see. Oh, it's coming, like, very good. So this is beautiful. You can see here, this everything is given, and total test of total effect is, and this is p value. It's coming significant. You can see p value is 0.003. It's coming significant. So intervention is very effective in in this, in these patients. Okay, whatever intervention we are giving, it's effective compared to control group, to reduce the incidence or prevalence of lymphedema in post breast survivor patients. Okay, that is something. So we have to give. Okay, I think. And please perform other for others, like two group mean comparison, one mean comparison. I have given all the codes, and in group we will see, you can just run all the things. You will get DY plot, funnel plot, you will give. Okay, all the things. This is a just you have to select and you have to perform. If you feel any face any problem, please contact to me. Thank you very much, ma'am. I think I have to stop here.
Thank you, sir,
I think there's a lot
for
of
an
questions.
enlightening session on meta-analysis using our studio. Your expertise and in-depth explanation have provided us with valuable insights into statistical modeling and evidence synthesis. We truly appreciate your time and knowledge in guiding us through this essential aspect of research, sir. So
Thank
also
you.
there are some queries from participants.
Yes, yes,
I would
yes,
like to request you please address.
yes.
There is one question that is, which version should be used, R 4.4.2 or R 4.4.3? Also, why knowledge P?
Why knowledge?
Why
I
knowledge?
have explained all the things. There is no, you can give any name, prevalence, whatever you can give any name. There is no problem. It's up to you. Okay,
And
there is no
which?
problem. But version, whatever version you have, you will do this meta
Okay,
analysis. There is no problem.
okay,
Okay,
okay.
if you face any problem, you can contact me. There is no, okay. But you have
Uh,
to remember, R is case sensitive. So if you
okay.
have given like m dot bin in small letters, then you have to again write m dot bin in small letters. If you write down m in capital letter, then you perform, it will not work. So earlier you have given in your command m dot bin. Okay, then in a second command, if you write down m capital and bin, it will not work. Yes, ma'am.
Uh, what is pooled effect? Is it where most of the data is concentrated?
Yes, ma'am.
Uh, what what is pooled effect? Is it
Overall effect.
where?
Overall effect. That is the overall effect. Okay.
Okay.
Yes. It is overall
So
effect of some units.
meta-analysis can be best done for which type of studies? RCTs or descriptive studies or any?
Any study in R, any study in Railman, there is no for like observational study, there is no till date, there is no option for this, for observational descriptive one group analysis, one group mean and one group this proportion. There is no any I think facility in Railman, but in R it is you can do, we can do here in R studio. Okay, in any
Um,
network meta analysis you can do, there is no problem.
okay. How will we create codes for our study? And also, what is publication bias?
I think I have there is a publication bias, man. For example, because we can see here positive results are publishing, okay. But if there is a negative result, means if there is no effect of, so the journals are not publishing these results. So ever all the results with positive effect, okay, they got significantly. So when we do meta analysis and all the studies have positive effect, okay, significantly, so there is a publication bias because there is no negative study over there. So this is, so there is there in in meta analysis, there should be balance, negative study and positive study. So I think like nowadays general are accepting negative study also. So there is one journal which is accepting only negative studies. Okay. So this is we can remove publication bias.
Okay, thank you, Dr. Ashok sir, for addressing the queries. I hope all the participants found your explanation helpful and gained clarity on their doubts.
Yeah,
Thank you,
if
sir.
they have any problem, they can ask me on my WhatsApp number in group. We can help. When you do on work on R Studio, you will get problem. When you will get problem, you will learn. Otherwise, you will not learn. Okay, if you will not get any problem in R Studio, you will never learn. But if you
Yes, sir.
get a problem by doing this, you will definitely will learn lot of things. Yes, this I think Shivani Badonia. You can like WhatsApp me, okay? You can directly WhatsApp me. We will solve. We can have a like Zoom meeting separately. Then I will solve your problem. Okay? Yes.
Thank you, sir, for your
Thank you. Thank you.
wonderful insights on this topic. Thank
Thank
you, sir.
you.
After an insightful session on meta-analysis, we now move on to our second speaker, Dr. Ramesh Pal, who will be discussing heterogeneity, sensitivity, and subgroup analysis. Dr. Pal is an assistant professor in Department of Endocrinology at PGIMR Chandigarh with extensive research expertise in metabolic bone disorders, osteoporosis, sarcopenia, and type 2 diabetes. He has been recognized with several prestigious awards, including the Young Investigator Award, the C. Vene Barden International Travel Award. His contributions to endocrinology and evidence based research are highly commendable, and we are honored to have him with us today. Without further ado, I now invite Dr. Ramesh Pal to take over the session. So, please.
Good evening. Good evening, everyone. Thank you, Dr. Priyanka, for the introduction. So, without wasting time, I will share my slides, and I thank the participants for staying back. I mean, a count of more than 130, even on the penultimate day of this marathon workshop. I mean, speaks a lot. Are my slides visible?
Yes, sir.
Are they in the slideshow mode? Just a
No.
minute. Yeah, just a minute. Are they in the slideshow mode now?
Yes, sir.
Okay, thank you. Am I audible? I hope I'm audible as well.
Yeah, yes, sir, you are.
Right. So I will move ahead. So the basics has already been covered in the previous 5 days, and a lot has been taught today by Dr. Ashok. So I declare that I do not have any conflicts of interest to declare. So I will be covering the following topics one after the other: the basics of heterogeneity, how to assess heterogeneity, how to address heterogeneity once you have assessed it, and the other two topics, that is sensitivity and subgroup analysis. So what you can see here, so you can see that there are multiple beads, but are the beads all similar? No. So the beads are varying in color. Definitely they're varying in color, and as you can see, the beads are varying in sizes as well. So this is what heterogeneity is all about. Heterogeneity is about dissimilarity. In other words, you can say heterogeneity is nothing but dissimilarity, or rather, and homogeneity is similarity. So you can consider this, you can compare these beads with multiple studies that are being included in a meta-analysis. So apparently all the studies appear similar, but if you look properly, the studies are different in terms of, here in terms of color. If you consider a study, they will differ in terms of participant inclusion criteria, exclusion criteria, number of participants, outcomes, statistical methods used, and this is what heterogeneity is all about, and this heterogeneity affects the final results of a meta-analysis. So coming on to the basics of a meta-analysis. So in meta-analysis, a meta-analysis includes multiple studies, but all the studies are looking into a, I will just use a laser pointer. Yeah. So all the studies are looking into a specific outcome of interest. So if you look into, so I will narrate it with an example in the next slide. However, each study has its own effect size. What meta-analysis software does, so may it be a R, or may it be R Studio or a Raveman. Meta-analysis assigns a weightage to each study, and based on the weightage, meta-analysis generates a pooled effect size. So someone was asking what is mean by pooled. Pooled is basically all the, so if you have included 10 studies, each study will have its own weightage. Suppose we are looking, so in, let's say that the effect size is a relative risk, as Dr. Ashok was talking about in his in his analysis. Each of the 10 studies will have its own relative risk. Meta-analysis will assign a weight to each of the 10 studies, and based on the weight, meta-analysis will generate a pooled relative risk. We often use the word, we often replace the word pooled with summary or overall. Pooled relative risk, or a summary relative risk, or a overall relative risk. So this is one of the meta-analysis which we had published a few, maybe a couple of years back. Here we had compared the effect of one class of drug, that is sodium glucose cotransport inhibitors, co-transporter 2 inhibitors, on the effect of gout. So as you can see here, so these are the five randomized control trials which we had included. You can see 5 studies. So these are the effect size of individual studies, or if you look into the forest plot, these red boxes represent the effect size of individual studies with their 95% confidence intervals. And what meta-analysis software is doing is that it is generating a pooled effect size represented in the form of a diagram, pooled effect size along with its 95% confidence interval, after it has assigned a weight to each of the individual 5 studies. So this is what meta-analysis is all about. Studies. Each study has its own effect size. The meta-analysis software assigns a weight to each of the included studies, and based on the weight and based on the individual effect size, the meta-analysis software generates a pooled effect size. So this is the pooled effect size along with its 95% confidence interval. So what is heterogeneity? So the as you can, if I go back, so the yeah, as you can see, the effect size is not similar. The effect size, as you can see over here, it is widely varying between these 5 studies. Although they are on the same side of this line, even then the confidence intervals of these 5 studies are not overlapping. So the effect size would definitely vary across studies. This is almost inevitable. And if you compare this to forest plot, here you can see the effect size of the individual 5 studies are very similar to each other. So their confidence intervals are almost overlapping with each other. However, if you see here, if you see over, if you look into this forest plot, the effect size of the individual studies are completely haywire. Like one is on one side of this line, one is on the other side of this line, and even if they are on one side of this line, their confidence intervals are not overlapping. So we can see that the effect size of the individual studies are extremely variable. As you can see here, the effect sizes are very similar and the effect sizes are very dissimilar. So this is what heterogeneity is all about, and this is called statistical heterogeneity. It is a variation of the individual study effect sizes that are included in a meta-analysis. So statistical heterogeneity can be divided into two categories. It could be clinical heterogeneity, as I was saying, that can arise out of differences in the inclusion and exclusion criteria resulting in different study participants, resulting from different interventions, and resulting from different outcomes being studied. Or it could be a methodological heterogeneity that could arise because of a basic variation in the study design, or because of the risk of bias of the studies included. So overall, we will not separately deal with these two aspects. We will only deal with the overall entity called heterogeneity, and that will include both clinical and methodological heterogeneity. So heterogeneity, as I said, it is almost invariably present in all meta-analysis, because it is very unlikely that all the included studies will have the same effect size. So it is almost inevitable that heterogeneity will creep in all meta-analysis being conducted. However, the problem is when the heterogeneity is the amount of the heterogeneity is too large. So when too much heterogeneity can be concerning. it can imply, if the heterogeneity is too large, it means that the studies are not similar enough to be included in the same meta-analysis. So in meta-analysis, we quantitatively synthesize the data and generate a new data. So when the studies are not very similar, not or rather highly dissimilar, it would be unfair to conduct a meta-analysis. And and even if we conduct a meta-analysis based on in studies that show significant heterogeneity, the it could, I mean, there could be significant error around the pooled effect size. So obviously you can pool together any an n number of studies, but if you find that if there is significant heterogeneity, the pooled effect size that will be generated, of course meta-analysis software will generate a pooled effect size, but you have to take that pooled effect size or take that data with a pinch of salt rather than accepting it right away. So what are the methods for assessing heterogeneity? The methods that are commonly used are the Cochrane's Q test, the Higgins I-squared statistics, and prediction interval. I'm very sure most of the audience, almost 100% of the audience would have heard of Higgins I-squared statistics, and I'm very sure, more than half of the audience would not have heard about the other two, the first and the third. So I-squared is commonly used, and the other two are not given that of a preference, which is actually wrong. So before I go into these three methods, one thing that we should know about, because one thing that we need to be clear about is what is the true and observed effect size. So each and every meta-analysis that is conducted has something called a true effect size and an observed effect size. So the true effect size implies, so it is the effect size that a study would report if that study had been conducted in an ideal scenario. So what would be an ideal scenario? An ideal scenario would be an infinitely large sample size and with no errors. But however, that is, as I said, that's an ideal scenario, and that cannot be replicated, and that cannot be replicated in probably any study. So what we get out of an individual study is an observed effect size. An observed effect size is the effect size that the study actually reports. And invariably, the observed effect size differs from the true effect size. So it will fall below or it will be above the true effect size due to some sort of sampling error. So we should keep these two things in mind before we proceed forward. That is true effect size and observed effect size. And lastly, the one basic thing that we need to know about null hypothesis. So the cornerstone of any statistical analysis, null hypothesis. So null hypothesis, we keep any research question, whenever we keep any research question in mind, we also keep a null hypothesis in mind. And at the end of the study, we have to, our objective is to either accept or reject the null hypothesis. Similarly, in meta-analysis, there is something called a null hypothesis. The null hypothesis in a meta-analysis states that the true effect of the intervention that is being studied by the meta-analysis is the same across all the studies included, and the variations that are observed amongst the studies are simply due to chance or simply due to random error. So, this is very similar to the null hypothesis that we describe in case of individual studies. So, in the subsequent slides, we will come to know that methods for assessing heterogeneity or methods for addressing heterogeneity keeps this null hypothesis in mind and tries to accept or reject this null hypothesis based on the statistical analysis. So what is Cochrane's Q test? So as I said, there are three major ways of assessing assessing heterogeneity. The first is the Cochrane Q test. So it tests the null hypothesis that all the studies share a common effect size. So Cochrane's Q test starts with the hypothesis that starts with the fact that the null hypothesis is true, right? And if the null hypothesis is true, there will be if the null hypothesis is accepted at the end of Cochrane's Q test, there will be no heterogeneity. And if the null hypothesis is rejected at the end of Cochrane's Q test, there will be some heterogeneity. So it is calculated. So the calculation is a bit complex. You may not even try to keep this in mind, but being here, I will have to explain. At the end of the day, everything is generated by the statistical software that you're using. So it will be prominent if I show this equation. So it is calculated as a sum of the squares of the differences between the effect size of each study and the summary effect measure. So the summary effect measure is a pooled effect measure that is being generated by the meta-analysis software. And it is calculated according to the fixed effect model, weighing each difference by the contribution of each study to the summary effect result. So if you look here, so the Q is the thing that is being generated. The Q is the Cochrane Q that is being generated. So theta is the summary effect size or the overall effect size that is being generated by the meta-analysis software. Theta k is the effect size of individual study, and the theta k is different for different study. I hope it is clear by now. Capital K represents the number of studies, small k represents each individual study, and WK represents the weight of each study. So it is in other words, you can say it is a weighted sum of squares of the differences between. So what we are generating here, we are generating a difference between the effect size of individual study when compared to the overall effect size. It is being multiplied by the weight of the study, squared and multiplied by the weight of the study, and it is summed for the individual study. I mean, if k is 10, so it will be summed up 10 times. This is what Cochrane's Q test is all about. This is what the software does. None of us need to do this. It is just to iterate what this Cochrane's Q test is all about. One thing I didn't highlight rather. So this Cochrane's Q test is based on the fact that we are using a fixed effect model. I will let you know about. Dr. Ashok had been talking about this in his presentation. I will deal about it further in the subsequent slides. Just to keep in mind that this Q test is based on the fixed effect model, not the random effect model. So Q statistics, you all know in some of the softwares, this Q statistics is not represented as Q. Rather, in Revman, it is represented as a chi-squared. It is represented as a chi-square or this chi-square because it follows a chi-square distribution. And how to interpret this Cochrane's Q test? Again, yeah, because the interpretation has to be done by you. I mean, that will not be done by the software. So for interpretation, you need to know the degrees of freedom. So what is degree of freedom from a basic statistics knowledge? Degree of freedom is equal to the number of studies minus 1. So if Q minus the degree of freedom, in other words, if the degree of freedom is more than the Q value, then the difference will be less than 0. Then null hypothesis holds true, as I was saying, and there is no excess heterogeneity beyond that would be expected by random or chance. However, if Q minus DF, or if the degrees of freedom, or if Q is more than the degrees of freedom, then null hypothesis is rejected, and we can infer that the excess variation or in the effect size among the studies can be attributed to sources of clinical and methodological heterogeneity beyond that of chance. In simple words, if the Q is more than the degrees of freedom, we conclude that there is statistical heterogeneity in this analysis. We also look into the p-value of this Q test. So in general we take a significant p-value of less than 0.05. However, when we use the chi-square statistics or this Q statistics, when the number of studies are less, so this chi-square statistics is less powered. So the power of this Q test is less when the number of studies are small. So for the Q statistics, we take a p-value of 0.1 rather than 0.05. Right. You can take a p-value of 0.05 when the number of studies are large. I don't know what is the cutoff. I don't know it. And I'm sure that the number of studies have not been defined. Like if there are more than 10 studies or 15 studies, but for safety sake or just for to be safe, it is recommended that you take a p-value of less than 0.1 when considering significance with regard to Q statistics or other Q test. So this was one of the meta-analysis which we had conducted a few years back during COVID times. So we had looked into the effectiveness of statins in improving clinical outcomes in COVID-19 patients. So as you can see here, so we had done two analyses actually. So I will just So here you can see here. So we had included 5 studies in this analysis. Here the effect size is odds ratio, and we have generated a pooled odds ratio which is 0.51. apparently it looks to be. So I will not go into whether this effect size is statistically significant. I will go into the I will look into whether the heterogeneity, I mean, I will look into the heterogeneity aspect of this analysis. You can see here the chi-square, as I was saying, it has been represented by chi-square, not by q. Chi-square is 3.86. The degree of freedom is 4. So if you subtract chi-square minus 4, it comes out to be less than 0. Hence, you can infer that there is no significant heterogeneity, which is further reinforced by the fact that the p-value is not less than 0.1. Hence, we can confer that the this that there is no significant statistical heterogeneity in this analysis. However, if you look into another analysis, here we analyze studies where they had represented the data in terms of hazard ratio. So you cannot pool hazard ratio and odds ratio together. So we had to analyze them. We had to analyze them separately. Just a minute. Yeah, we had to analyze them separately. When we pool together the hazard ratio, we found that we again generated a pooled effect size, a pooled hazard ratio. However, when we looked into the heterogeneity aspect, the chi-square was 13 with a degree of freedom of 3. Here, if we subtract chi-square from degree of freedom, it turns out to be around 10, which is more than 0, which is substantiated by the fact that the p-value is significant, which is less than 0.1, thereby implying that there is significant heterogeneity in this analysis. However, there is no significant statistical heterogeneity in this analysis. So q minus def less than 0, p more than 1.1. No statistical heterogeneity, no significant statistical heterogeneity. I should use the word significant. Here q minus df more than 0, p less than 0.1, implying significant statistical heterogeneity. I hope this example would have clarified some of your doubts. So now I will look into the second aspect of second the second way of assessing heterogeneity, that is Higgins I-square statistics. As I said, you all must be aware of this. You all must be using this. So again, a little bit of theory before I look into the practical aspect. So it quantifies. So it is a percentage. You all know that it's a percentage. It's not an absolute value. On the contrary, Q is an absolute value. Cochrane's Q statistic is an absolute value. I-square is a percentage. It quantifies the percentage of variation across studies. The variation across studies will be called between study variance. That is due to unexplained heterogeneity rather than by chance. In other words, if I-square is more than 50%, it means that more than 50% of the between study variance that is generated by the meta-analysis is due to unexplained heterogeneity and not due to chance. So if I-square is suppose 75%, it means that 75% of the between study variance is explained by it is contributed by unexplained heterogeneity and not by random chance. So simple. So it just explains the percentage of the variance that is being explained by heterogeneity, but it does not actually mean it doesn't actually quantify the amount of heterogeneity. This is a basic flaw that we all make. So again, the formula the employed is q minus k minus 1. Again, k is the number of studies. Q is based on the chi-square statistics that we showed in our last slides. Q minus k minus 1 by q into 100. So when you multiply by 100, you generate a percentage. So you might wonder if q minus, so k minus 1 is nothing but the degrees of freedom. It is actually q minus degrees of freedom by q. So if degree of freedom is more than q, then q minus degree of freedom would become negative, right? Right, as we showed in our previous slide. But here, if q minus degree of freedom is negative, we consider it as 0 rather than considering it as negative. So the minimum value of I-square is 0 and not minus 10 or something. Again, I will go back to the same meta-analysis, the same analysis. So I intentionally skipped this I-square part. So as you can see here, the I-square is 0. So if you put the values, so 3.86 minus 4, it will be something around minus 0.14. The value should have been in negative, but as I said, if the value is in negative, we take it as 0 and proceed forward. So the I-square turns out to be 0 in this scenario. So traditionally, we all have been using I-square for categorizing heterogeneity. Even I have been using it, a very honest confession. So roughly we use this cutoffs 25 to 50% we say low heterogeneity, 50 to 75 moderate heterogeneity, and more than 75 high heterogeneity. Again, these cutoffs are extremely arbitrary, and this is something that has been taught, that has been propagated, but there is no strong evidence behind it. But as I said, is this the right practice of categorizing heterogeneity? No, this is actually not the right practice, because I-square statistics is full of fallacies, full of loopholes. As I said, I-square is a proportion, it is not an absolute value. So since it is a proportion, it is a proportion of how much between study variance is being explained by or rather contributed by heterogeneity. It is not an absolute measure of heterogeneity. Actually, it doesn't tell us how much the effect size. It doesn't tell us about the actual amount of between study variance. In other words, the actual amount of between study variance is expressed by Q statistics, not by I-square statistics. It doesn't reflect the actual amount of dispersion of the studies. It doesn't provide information about the cause of heterogeneity. So I-square, the routine practice of using I-square statistics for defining heterogeneity is flawed. And most of us often say that that the heterogeneity while writing the statistical analysis part, the heterogeneity of data was assessed by I-square statistics, and I-square value of more than 75 was considered to be statistically significant with a p-value of less than 0.05. So the basic flaw is that I-square statistics doesn't have a p-value. The p-value that we are talking about is of the Q statistics, not the I-square statistics. So this sort of, I mean, I have seen it in multiple meta-analysis. I'm very sure even some of the reviewers that review meta-analysis are not aware of this. I'm sorry to say this, but this is a fact. And this is an entirely wrong practice. So the p-value that we talk about is of Q statistics, not of I-square statistics. And we should refrain from using this sort of statement, in the future. So again, so if you look into this, so if you look into the same meta-analysis where we have pooled the hazard ratios, here you can see that the I-square is 77%, and and obviously, and looking into the chi-square value and the p-value, there is significant statistical heterogeneity. But what do we gain from this I-square value from this forest plot? What we can say is that 77% of the between study variance is due to unexplained heterogeneity. That's all we can comment from this forest plot. The I-square doesn't tell anything about the exact between study variance. It doesn't tell about the exact value of heterogeneity or the exact amount of heterogeneity. It doesn't tell if the between study variance is statistically significant. The p-value is not pertaining to I-square. It is pertaining to Q statistics, and it certainly doesn't tell us about the causes of heterogeneity. That's all. So the I-square, I'm not sure why is it reported so often. Probably it has been going on. That's why all meta-analysis software reports I-square. Probably it's more appealing to the eyes, as I said. But interpreting heterogeneity solely on the basis of I-square is wrong. Yes, you can comment on I-square along with the Q statistics and the p-value of Q statistics, but commenting on heterogeneity solely on I-square is entirely a wrong statistical maneuver. So one word about tau square statistics, because tau square, it does give us some idea about heterogeneity. So tau square is an estimate of the between study variance in a random effect model meta-analysis. So here you can see, so tau square, like Q statistics, it gives us an absolute value of the between study variance. However, it is useful only in a random effect model, not in a fixed effect model. I will show you. I will show how. What is the implication of this? So it quantifies heterogeneity of the true effect size across studies. A larger tau square value indicates greater variation in the true effect size across studies, indicating more heterogeneity. However, there is no straight cutoff to define heterogeneity based on tau square. It simply means a larger tau square means greater heterogeneity, but we cannot just like I square, more than 50%, more than 70%. There is no straight cutoff beyond which you can say that heterogeneity is statistically significant to be worried about. Again, the same meta-analysis. I'm sorry for clinging to the same thing over and over again, because this is perhaps the best example I can show you. If you look into this forest plot or this analysis using odds ratio, I have used a fixed effect model, and here you can see that when you use a fixed effect model, it doesn't generate a tau square. So as I said, tau square, it comes into picture only when you use a only when you use a random effect model, right? So this fixed effect model did not generate a tau square. However, when we pulled together the hazard ratio, we had to use a random effect model because of the heterogeneity. I will talk about it when we will talk about how to address heterogeneity. That generated a tau square value. Now the tau square seems to be very innocent. It seems to be very like it seems to 0.1. So, but based on that, since it doesn't have any particular cutoff, you cannot say heterogeneity is more based on the cutoff. Possibly tau square of 0.1 is probably large for this meta-analysis, so as to imply that heterogeneity is statistically significant. Another example, here we looked into the risk of fractures in a endocrine entity called hypoparathyroidism, where Ashok sir was one of our collaborators. So here we have here as you can see, uh, yeah, here you can see. So here we had used a random effect model, and we had performed a subgroup analysis looking into the fracture risk in hypoparathyroid patients who had a non-surgical cause of hypopara versus those who had a post-surgical cause of hypopara. Here you can see the tau square value is, sorry, the tau square value is 0.01. This tau square value is low, resulting in a and which is corroborated by the fact that the chi-square value is also suggestive of no significant heterogeneity. However, when we consider post-surgical hypopara patient, chi-square suggested a significant heterogeneity, and the tau square value of 0.94 also suggested significant heterogeneity. So the exact value of tau square, I mean, you cannot what I mean to say that there is no definite cutoff beyond which you can say that tau square is significant, but compared to 0.01, definitely 0.94 is higher. Hence, 0.94 suggests significant heterogeneity compared to 0.01. Again, when we I'm sorry. So in this we were looking into vertebral fractures. And now in this analysis we were looking into humeral fractures, upper limb fractures. So yeah, you can see here that. I will just yeah. Here you can see the heterogeneity. Here the tau square is 3.32, 3.32 and chi-square is also suggestive of significant heterogeneity. Here you can see the tau square is 4.15, and chi-square is also suggesting significant heterogeneity. So a tau square value, both 4 and 3, both are implying significant heterogeneity. So tau square, a high value of tau square implies significant heterogeneity, as simple as that. However, there is no specific cutoff value beyond which you can say that you cannot say a tau square value of more than 1 signifies heterogeneity. Tau square value again has to be interpreted in line with the chi-square value to say whether heterogeneity is present or not. And the last method for assessing heterogeneity is prediction interval. Dr. Ashok was talking about it in his last few slides. So prediction interval is possibly the best method for assessing heterogeneity. So by definition, it is defined as an interval. It is somewhat like a confidence interval, but not a confidence interval. So it is defined as an interval within which the effect size of a new study would fall if this study was selected at random from the same population of studies already included in the meta-analysis. So you conduct a meta-analysis, you get a prediction interval. As an example, so it is a perfect measure of dispersion. Let us assume, so just like confidence interval, prediction interval is also expressed as a 95% prediction interval. Let's assume that for one meta-analysis, the 95% prediction interval is 1.08 to 4.16. Suppose this is an odds ratio. We generate a 95% prediction interval of odds ratio 1.08 to 4.16. It means that if we select any comparable study, like any study which is comparable to the studies that we have included in the meta-analysis at random from the world literature, the effect size is likely to fall between this range of 1.08 to 4.16, and you can say this with 95% of confidence in 95% of the times. Right. So a wider confidence interval means more statistical heterogeneity. That's it. So how does it differ from confidence interval? So confidence interval is a measure of precision. It means with what precision you have measured, or you have calculated the summary, with what precision you have calculated the effect size. On the other hand, prediction interval is a measure of dispersion. This measures of a measure of prediction is confidence interval. Measure of dispersion is prediction interval. How dispersed are the studies included in the meta-analysis? In simple words. So this was a recent meta-analysis that we published, where we looked into fracture risk in patients with adrenal adenoma. We have an endocrine organ called adrenal gland that may develop a tumorous malformation resulting in adenoma, and that might secrete some hormones. So what are the risk of fracture? So here we here and this we performed using R. The previous meta-analysis we performed using Revman. So Revman, to the best of my knowledge, does not generate a prediction interval. However, R generates a prediction interval. You can see here. So this represents we performed a proportional meta-analysis. I think Dr. Ashok was talking about it. Here we try to find out the proportion of, or rather the prevalence of fractures based on individual studies. So this was looking into vertebral fractures, and this was looking into all fractures. As you can see here, so you can very well appreciate by looking into this forest plot. It doesn't require very rocket science actually. It's called eyeballing. If you eyeball, it is very obvious that the studies are are highly variable. Accordingly, you can see here that the prediction interval is so wide. It's from 0 to 1. I mean, you cannot have a prediction interval wider than this. So if you include any study, any future study that will be published based on, looking into fracture risk in adrenal adenomas, it is very obvious that it will fall in this prediction interval. Again here, when we looked into all fractures, we found that the prediction interval was very wide. It is very obvious because the effect size of the individual studies were highly variable. Yep, as you can so this is prediction interval should be used. It is a state of the art, and this is probably the best method of representing heterogeneity. So having assessed heterogeneity, we need to address it. How we can address it? One of the best way to address heterogeneity is to choose the appropriate meta-analysis model. Here we will talk about random effect model and fixed effect model. Assess outliers, and you can remove them. Here, this implies sensitivity analysis. Explore heterogeneity by something called moderator analysis. By moderator analysis, we mean subgroup analysis and meta regression. We'll be talking about subgroup analysis. Meta regression I will skip for the sake of time. And at the end of the day, when we are fed up, we don't have any other means of addressing heterogeneity. Like in our previous model, we didn't have any means of addressing heterogeneity. We simply acknowledged it in the limitation section of the manuscript. Write one page limitation, so and so. And I hope you will be able to satisfy the reviewer. So choosing the appropriate model. So fixed effect model versus random effect model. So I will just skip these two slides for the sake of time, and I will just come to the comparative aspect. So a fixed effect model and random effect model. A fixed effect model assumes that the true effect size is identical for all the studies. All the studies. However, random effect model assumes that the true effect size is different for different studies. So a random effect model is more of an ideal scenario, or rather real life scenario or real world scenario, than the fixed effect model. In case of weightage of individual studies, a fixed effect model gives larger weightage to a studies having a larger sample size. Rather, larger studies gets a higher weightage, smaller studies get a lower weightage. Accordingly, smaller studies will not be represented to that extent in a fixed effect model. However, in a random effect model, larger studies are given a relatively lower weight. It doesn't mean weight. You should emphasize on the word relatively lower weight, relative to a fixed effect model. It doesn't mean that a larger study will be given a weight less than a smaller study. But yes, in a random effect model, a larger study will be given a weight which is relatively less as compared to that which would be assigned by a fixed effect model, while a smaller study will be given a relatively higher weight as compared to that assigned by a fixed effect model. So the fixed effect model tests for the null effect in each included study, while in random effect model, it tests the hypothesis that the mean effect derived from the observed result is null. Choice: you should choose a fixed effect model when the included studies are homogeneous. You should choose a random effect model when the included studies are heterogeneous. Probably, so this is the takeaway point from this. I'm so sorry. So this is a takeaway for a point from this table. You choose a fixed effect model when you suspect that the studies are homogeneous. You choose a random effect model when you suspect that the studies are heterogeneous. Mark my words that I'm using the word suspect, and I will tell you why I'm using the word suspect. And accordingly, if you use a random effect model, the confidence interval will be very narrow. You will be tight. While in a random effect model, the confidence interval would be wide, because a wider confidence interval means the results are more generalizable, and you can generalize that results to more number of studies. So in a real world scenario, if you are not sure about heterogeneity, always choose random effect model over fixed effect model. That will give you a result that is more generalizable and more authentic, I would say, rather than a fixed effect model. So this is an example of the same. This is an example. So I had, so this is not this is a study which I have taken from, which I've borrowed. I mean borrowed from the internet. So here the same analysis. So the risk ratio has been pooled from 3 different studies using our fixed effect model and a random effect model, one after the other. You can see when the fixed effect model. So here you can see the heterogeneity is the heterogeneity is statistically significant. I mean, sorry, the so I mean, so when we're using a fixed effect model, it is generating a just a minute. Yeah, it is generating a pooled effect which is zero 0.6 with a very narrow confidence interval, as you can as you can gauge from the shape of the diamond. However, when we're using a random effect model, the overall pooled effect is different, and the shape of the diamond also gets wide because of the wider confidence interval. In fact, the significance is lost, as you can see from this Z statistics. P value is significant. The significance is lost because the confidence interval crosses 1. Significant. So as I said, since there is significant statistical heterogeneity, I mean, if you look into the weightage of the studies, just a minute. So this study by Dona et al. That had the largest number of participants. It was given a weightage of 51. When we use a random effect model, the weightage was relatively reduced, 43. On the contrary, this study by Odium et al. That had a number of participants, although large, the number of participants were less than Donna et al. It received a weightage of 33% nearly with fixed effect model. However, it received a weightage of 42% when using a random effect model. So this is how random and fixed effect models vary. Again, we need not go into the analysis part of it. You simply have to choose the model, and the software will do the rest for you. But the biggest part is when and what model to choose. So I mean, you should not target to choose the best model to fit your analysis. That is not the right strategy. The crucial is to it is important to decide which model best suits the question being assessed. You should be able to judge the heterogeneity based on the studies itself, like based on the participants, inclusion and exclusion criteria, intervention being carried out, the comparison being looked into, the study design, the study settings, etc., the duration of the studies. If the studies included in the meta-analysis are essentially similar based on the study characteristics, then fixed effect model is appropriate. However, this is rarely the case in a real world scenario. If the studies are considered to be heterogeneous, then random effect model is preferred, and the model should be decided before undertaking the meta-analysis. So while you are registering your meta-analysis in Prospero, you should preferably mention which model you should use. So we often, so in many of us while writing up a meta-analysis, we write that first we use a fixed effect model, but when we found that there was significant heterogeneity, we use a random effect model. So this practice is wrong. This practice should not be encouraged, because hereby we are deliberately using a model so as to deliberately reach at a conclusion. So this is not what why we should conduct a meta-analysis for. So temptation of choosing the model based on the statistical significance of heterogeneity should be avoided. The model should be decided a priori based on the characteristics of the studies being included, and it should be clearly mentioned in Prospero, and should be clearly mentioned in the statistical analysis part, and shifting from one model to another based on statistical heterogeneity should be avoided. So moving on to sensitivity and subgroup analysis. So both this analysis helps in picking out information which would otherwise be lost. So just one more basics of sensitivity analysis. So meta-analysis involve multiple assumptions to derive the primary results, but all these assumptions may not be correct. So sensitivity analysis is a repetition of the primary analysis we conduct the primary pooling once again with an altered data set to find out if altering any of the assumptions that we had made while conducting the meta-analysis, if altering any of the assumption changes the pooled effect estimate and hence the final conclusion. So in sensitivity analysis, we repeat the primary analysis by altering the data set, by removing one study, by removing two studies, maybe, or removing a certain set of studies. I will explain, and we find out if this deletion of studies makes any changes, makes any significant change to the pooled effect estimate. So the results of the meta-analysis is considered robust if they remain unchanged despite changes in assumption. Robustness is questionable if variations in assumption significantly changes the findings. So if we conduct a sensitivity analysis and we find that the pooled effect estimate is completely different from the one that was generated prior to the sensitivity analysis, in that scenario, you should take that meta-analysis with a pinch of salt. Consistency between the results of the primary analysis and the sensitivity analysis enhances the credibility of the results and the authenticity of the results. Sensitivity analysis should ideally be pre-specified. Should be pre-specified. As I said, just like you choose the model a priori, you should pre-specify the sensitivity analysis a priori, or it may be identified during the it may be identified during the review process. It can be identified during the review process. It can also be specified. It can also be pre-specified. However, if you pre-specify, it is better. However, it is not mandatory to be pre-specified. Unlike I will explain. So, what are the various steps where you can conduct a sensitivity analysis? So, sensitivity analysis can be conducted at all stages of the meta-analysis. So, while literature search, you can while searching a literature, you can make up your mind that I will perform a sensitivity analysis by excluding studies that has been published only as abstracts, because studies published only as abstracts often have loopholes. Like all abstracts are finally not published as a final paper. So including abstracts might include error to the final meta-analysis. So you can perform a sensitivity analysis by excluding studies that are published only as abstracts. You can perform meta-analysis based on the study design. You can exclude either observational studies or non-RCD studies from a meta-analysis, thereby generating a robust data based only on RCDs. You can perform meta-analysis you can perform a sensitivity analysis based on the eligibility criteria, like based on the participant characteristics, based on the intervention provided. Or you can perform a sensitivity analysis based on the method of analysis that is used by the individual studies, per protocol analysis. So you exclude studies that have been included as a per protocol analysis because it is said ITT is better than a per protocol analysis. And finally, you can conduct a sensitivity analysis based on the study heterogeneity. So as I said, so the second way of assessing heterogeneity is by removing outliers, that is by conducting a sensitivity analysis. So it is generally reported in a summary table. You may not generate a forest plot for individual sensitivity analysis. You may generate it. You may upload as a supplementary data, but it is sufficient if you report it in a summary table. So this was a meta-analysis which I had initially projected, where we looked into the gout outcomes with this class of drug, SGLT2 inhibitor versus placebo. Here you can see that we had included, again, the same thing. We had included five studies, but the point is that the different studies had used different drugs. This SGLT2 inhibitor is a name of a class of drug. So it has three main drugs in this. One is dapagliflozin. So these two trials by Butt et al. Had been conducted with the drug called dapagliflozin. The Canvas trial had been conducted with the drug called canagliflozin, while the EMPA-REG and the Emperor trial had been conducted by the drug called empagliflozin. So we thought of conducting if you see into this forest plot, you can see that the effect size with dapagliflozin and canagliflozin is much more than the effect size with empagliflozin. So we conducted a sensitivity analysis by excluding studies that had been conducted with empagliflozin. So we removed these two studies, conducted a sensitivity analysis. We found that the effect size was all the more increased. Rather, here we were able to conclude that SGLT2 inhibitors as a class reduces the risk of composite gout outcomes by 45%. 100 minus 55. Here we can say that SGLT2 inhibitors, we cannot say it's a class effect. We can say that dapagliflozin and canagliflozin reduces the risk of gout, gout outcomes by as much as 54%, from 45% to 54%. Also, you can see that by removing these two trials, the heterogeneity is the heterogeneity is significantly reduced. Heterogeneity is, the heterogeneity is completely obliterated. So here and also here we are able to compare the robustness of the result. Ultimately, the results, this result is ultimately supplementing the primary result, thereby also stating that our primary analysis is very authentic and very credible. This is a very nice meta-analysis actually, where sensitivity analysis has been depicted to its prime. Here the authors have looked into the effect of statins on cardiovascular disease. So this meta-analysis looks into the effect of statins on heart cardiovascular mortality. So these are the multiple trials that have been included, and the effect size that has been considered is a risk ratio, and a pooled effect size has been generated. Now, a multiple sensitivity analysis has been done. So I've highlighted these two trials, the ASCOT trial and the Jupiter trial. So the first sensitivity analysis was done by excluding these two trials. So these two trials were excluded because the trials had to be prematurely terminated at 2 years. So premature termination of a trial can lead to erroneous results. However, even after exclusion of the trials, the relative risk was 0.7. I will go back. The relative risk based on the primary analysis was 0.69. Based on the first sensitivity analysis, the relative risk was still 0.7, which is very close to 0.69. Subsequently, they excluded studies that had a high risk of bias. So out of the 10 studies, 5 had a high risk of bias, 5 had a low risk of bias. So when they analyzed those 5 studies, after excluding those at a high risk of bias, the relative risk was still 0.64, which is very close to 0.69. Thereafter, they excluded studies where patients had a prior cardiovascular disease. Again, they found that the relative risk was 0.62, very close to the 0.69. And finally, they excluded studies that had a duration of less than 3 years. Again, longer disease duration. A study that is conducted over a longer disease duration is likely to be more authentic than those having a shorter disease duration. So shorter duration. Again, they found the relative risk was very close to the primary analysis. So all these 4 sensitivity analysis complemented the primary analysis, and the results were very close to the primary analysis, thereby stating that the primary analysis is credible and the primary analysis is authentic. Primary analysis was robust. This is what we can infer from this. Now we'll move on to a subgroup analysis. I think it's almost time. I will just hurry through my slides. So the subgroup analysis means that a particular intervention, suppose statins, as I was talking about, statins in heart disease, the same intervention may not work uniformly across all participants. The intervention effect may vary across different participants. So male may respond to statin better than females. Those having a pre-existing heart disease may respond to statin better than those not having heart disease at this point of time. Those having diabetes may respond to statins better than those not having diabetes. So intrinsically, we are generating subgroups. So subgroups of participants may have a greater benefits compared to subgroups of participants who may not have that much of benefit. So this is the basis, this is the crux of subgroup analysis. So subgroup analysis here is helpful in identifying subgroup of participants that are more likely to benefit from an intervention, or may be harmful for them. Based on the intervention. It involves splitting the data from all participants into groups and analyzing the data separately. It sounds very simple. So conducting a subgroup analysis is vital if a specific group of participants in the study is expected to respond differently to an intervention based on a biological plausibility. So there should be a biological possibility behind it. We cannot simply state that statins is likely to be effective in patients having likely to reduce the risk of heart disease in patients who are having associated osteoporosis or bone disease. So there doesn't seem to be an underlying biological plausibility. But yes, those having underlying diabetes are more likely to have heart disease. So it is likely that statins are likely to be more beneficial in patients with diabetes for reducing heart disease than in patients without diabetes for reducing heart disease. So there is a biological plausibility behind this thinking, but there is no biological possibility behind the contrary thinking. So before you are thinking of performing a subgroup analysis, you should think that whether these subgroups are biologically plausible or biologically possible or not. So you can perform a subgroup based on the study design, RCT versus non-RCT, based on patient sex, male or female, ethnicity, Asian versus Caucasian, and based on the intervention type. As I said, different types of like statins, two types of statin. There are two types of statin broadly: lipophilic statin and hydrophilic statin. You may perform two subgroup analyses based on hydrophilic and lipophilic statin, and there is a biological plausibility behind it. Maybe lipophilic statins may get deposited in the heart plaques. Basically, they reduce plaque size and plaque rupture. They being lipid rich, they may get deposited in the plaque, and they may have a better effect than hydrophilic statins. I don't know. But there is still a biological reasoning behind it. Subgroup analysis is not for, but please note that it is not for searching a group showing a benefit in the study population when the overall results are negative. So if you find that, if you perform a primary analysis, if you find that the overall results are negative, still you are trying to do a subgroup analysis, that is entirely futile and that is wrong. That is called data dredging. The other thing, that is, you find that the results are significant, and you perform a subgroup analysis to find out which subgroup is beneficial. That is called data mining. You are mining out of data. You are like mining out other data from the primary analysis. But this is called data dredging, like खींचना, trying to stretch or drag करना, trying to stretch the data by inappropriate use of subgroup analysis to find out which subgroup is showing beneficial effect when the primary outcome is not significant. The primary outcome is not significant. You are performing a subgroup analysis that is statistically incorrect, and I'm very sure most of the reviewers will be aware of it and will be caught right away. So subgroup analysis, unlike sensitivity analysis, is always pre-planned. It should ideally be pre-planned. You can even consider post-hoc planning, but pre-planning is superior to post-hoc planning. Like as I said, the model, the type of the model, random versus fixed effect, should be decided prior to conducting the meta-analysis, or rather prior to conducting the statistical part of the analysis. Similarly, subgroup analysis should better be pre-planned. Like when you are writing when you are registering the data, the study in Prospero, you should preferably mention it a priori before conducting the meta-analysis per se. And it should preferably be conducted when the number of studies are more than 10. You have 4 studies who are conducting a subgroup analysis. That is ideally not correct. You may conduct, but that is not ideally the ideal thing. So how to interpret a subgroup analysis?
Sorry for interruption, sir, as
I'm
we are
almost done.
bound to
I think
time.
I can skip this part. So I will just take a couple of slides. So this is
Sure, sir.
just to give an example of a subgroup. Just as maybe a minute. Can I spare a minute?
So you can take
Yeah,
5
just a minute. Yeah,
minutes more.
I will just conclude in a minute. So, so this is a meta-analysis again during the COVID times when we looked into the effect of vitamin D on clinical outcomes in COVID. So here we conducted here we have taken the primary effect size as odds ratio and the pooled odds ratio. So here the primary analysis is statistically significant. So vitamin D reduces the risk of clinical outcomes by nearly 59%, right? Here, subsequently, we conducted a subgroup analysis. We looked into whether vitamin D given before the diagnosis of COVID is significant, or vitamin D given after the diagnosis of COVID is significant. So there was a biological reasoning behind it. So we thought that if we give vitamin D only after COVID, that is more likely to be beneficial than giving it prior to COVID. And accordingly we found that when we supplemented vitamin D after COVID, when vitamin D was supplemented after COVID, the results were statistically significant, and when vitamin D was given prior to COVID, the results were not statistically significant. And how to infer whether whether the two subgroups are statistically different? For that, we look here the test for subgroup differences. Here also the data is expressed as chi-square. Right. So I will skip this part. So even you can use subgroup analysis for looking into heterogeneity as well. So I will skip this part. So I will conclude by saying that heterogeneity is almost inevitable in all meta-analysis. It is omnipresent. Q statistics and prediction intervals should preferably be used for assessing heterogeneity. Undue emphasis on I-square should be avoided. And addressing heterogeneity by selecting the appropriate FE and RE model, but it should be decided a priori. Sensitivity analysis addresses heterogeneity. It reinforces the primary analysis. Subgroup analysis should also be selected a priori, but data bridging should be avoided. I will just want to emphasize on these two aspects. Do not lay too much emphasis on I square. Lay more emphasis on Q statistics and prediction interval, and try to select the best model. If you are not sure, best is select a random effect model. It will fit. Like a random effect model is like a one size fits all. You take a random effect model and you conduct a meta-analysis. You will get a data that is more generalizable and more reproducible, I would say, more acceptable and more digestible, more palatable. Thank you.
Thank you. Thank you so much, sir, for a highly engaging session. Your expertise has provided us with a deeper understanding of handling variability in meta-analysis, making our approach to systematic reviews more robust and precise. We truly appreciate your time and valuable insights. So before we begin with question answer session, as you know, after the completion of it, we will be sharing a Google form in the chat box, and this form contains 3 MCQs, and you will have 3 minutes to complete it. Now I would like to request Dr. Ramesh to please address the queries. So there is one question, which is a more robust measure of heterogeneity.
So most robust measure is prediction interval. But the point is that prediction interval is not always generated by most meta-analysis software. Like, as I said, to the best of my knowledge, Revman doesn't generate a prediction interval. For that, you need to have high-end softwares like R and R Studio. So if you're using R and R Studio, you should look into you should report the data as prediction interval. But if you're not using an R or R Studio, if you're using Revman, you should look into the chi-square statistics, the Q statistics, and not into I-square statistics. You can write I-square statistics along with Q statistics, but you should lay more emphasis on Q statistics and not I-square statistics.
In formula of I, we used Q. So isn't I square is extension of Cochrane, qualitative one?
I square is ultimately, as I said, I will go, I will explore, I will look at, I will show you this slide. I square is ultimately based on the Q statistics. If you look into this formula, am I visible here? So I square is just a minute. I will
Sir, your
close the
slide
chat
is
box.
showing some, yes, sir. Now
Yeah,
it's
sorry,
fine.
I had opened the chat box. Sorry. So I square is based on Q only, but here it is giving a proportion. It means what percentage of Q is being explained by heterogeneity. You understand? Like I hope I'm clear. So what percentage of this between study variance is explained by heterogeneity? As an example, suppose uh, you can have an I square of more than 75. If you can have an I square of say 25%, going by traditional teaching, I square 25% doesn't mean low heterogeneity. But even then, Q square, even if you based on Q statistics, the heterogeneity can be significant. Right. So it simply means that 25% of the heterogeneity or the 25% of the variance is explained by heterogeneity. It is not a measure of absolute, it's not absolute number. It doesn't mean that 25% is more. We traditionally use the cutoffs, but that is not the right way of explaining it. I square is derived from Q, but Q is much more informative and much better for assessing heterogeneity than I square. I hope I've been able to explain it. Ultimately, Q is everything. Q is letting you calculate I square. But I square, what you are generating from I square is a proportion, not an absolute value. And that cannot be representative of the absolute heterogeneity, actually.
Okay, sir. If prediction interval includes 0,
Yes,
does
it can
that
include,
it
as I
means
said.
significant heterogeneity and meta-analysis result is not reliable?
Sorry.
If prediction interval includes 0,
Yes,
does
you are
that
right.
it
Yes.
means significant heterogeneity and meta-analysis result is
Absolutely right.
not
As I
reliable?
said in this study, you can clearly see from here.
Yeah.
So there were multiple studies, and the prevalence of fractures reported in multiple studies were highly variable. But as I said, this doesn't require not it doesn't require if I hide this part as well, if I hide the heterogeneity tau square chi square prediction interval part, one can simply look and say that there is massive heterogeneity in the results, so which is reflected by the fact that prediction interval is including 0 as well as 1. So it is obvious that that there is significant heterogeneity when there is a wide prediction interval.
Okay, sir.
It is rather the width of the prediction interval that matters more rather than the an absolute number. I would say it is the width.
Okay, sir. How to interpret subgroup analysis?
Right, just a minute. I skipped that part actually because of shortage of time. Yes, I will just
Oh,
scroll down. Just a minute. Just a minute. Yes. So subgroup analysis, for that we look into, so this part actually I skipped that part. So for that we look into this part, test for subgroup significant differences. So if this so this so test for subgroup differences. So again, it starts with the null hypothesis that the two subgroups are not different. So by chi-square statistics, chi-square statistics has either to should either uphold the null hypothesis or refute it. Here, if you, as you can see, the chi-square value is not significant, so it doesn't it implies that there is that there is no significant difference between the two groups, right? So if it is statistically significant, it means that there is a difference between the two groups. For assessing, I mean, for looking into whether the two groups are different, we simply have to look into test for subgroup differences in this. I don't have a better example for this actually. I don't have a better example for this. I don't have an example where the data is significant as of now, where the two groups are statistically significant. I mean, sorry.
Uh, can you please tell how to generate prediction interval in R Studio?
I think it was already covered by Dr. Ashok. It was
Okay,
already covered by Dr. Ashok. It will be difficult for
Mhm.
me to generate here actually.
Yes, sir. Yes, sir. I have
Yes, Dr.
covered.
Ashok
I
has
have
already
given
shown.
command also.
Okay,
They
okay.
can generate themselves.
Yes, 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 yes. Even I don't have R in this actually in this computer actually. It doesn't support R. That's why.
Mm, okay, okay, sir.
It has already been shown, and if I start, it will take another 15-20 minutes actually.
Uh,
And Dr. Ashok will be able to has already shown it and probably has dropped shared the instructions as well, commands
sure,
as
sir.
well.
Yes, sir. Um, thank you, sir, for
Thank you.
addressing the queries. I hope the participant found your explanations helpful and gained clarity on their doubts. Thank you once again, sir.
Thank you so much. Thank you. Have a good night. Thank you.
Thank you.
Thank you, sir. Thank you. Thank you very much.
Thank you, Ashok ji. Thank you, Ashok
Nice
sir. Good night.
presentation.
Good night.
Yes, sir. Thank you.
Good night. Now I would like to request technical team, please share the link, and participants, please complete this form within 3 minutes.
MCQ link has been sent by technical parts. Please attempt.